Okay, so we've spent time learning about Kc, equilibrium constant, that uses concentration. That's what the little c stands for, is concentration. All the things we've done so far have used molarities. And everything we've done so far, we've been solving for Kc. I told you way back at the very beginning that there's a lot of Ks. Sometimes they just call it K. There's no little subscript on it. Most of the time when we're doing concentration, they call it Kc. But there's actually some others as well. If you look right here, I've got a list of all the Ks we will be learning this year. So the first one, Kc, is the one we've been doing. That's the one that is based on concentration. What we're going to cover next is Kc, and the little p is for pressure. So Kp we will be doing for gas phase reactions, and we'll be studying and plugging in plugging in pressures instead of concentrations. But the great news is it really is no different. And in this lesson, I'm also going to teach you how these two relate to each other for gas phase reactions. We will eventually, that's actually this unit, actually this one's part of this unit too, KSP. The KSP, the little SP, stands for something called solubility product, and that's going to be a special group of equations that involve the dissolving of solids. So we'll get into that in a couple of days. These two right here are actually next unit. Okay, so you see next unit we will definitely be sticking with Ks and equilibrium constants. The little A stands for acid and the little B stands for base, because the next unit we're going to do is called acid-base equilibrium. So again, today's focus is going to be about pressure and Kp. Now, it says on your notes, and this is important to know, that we're only going to be asked to do Kps for things that are gases. It doesn't make sense to do Kp for anything other than that, because pressure is a variable that we use to measure for gases. You know, your solids and your liquids, although they physically exert pressure, it doesn't ever change because they are not compressible. So I want to show you what Kp looks like in comparison with a Kc, so I can again make the point that it's going to be super easy transition from Kc into Kp. So let's say we had this equation on a test or a homework or whatever, and I was asking you to do a Kc problem. The Kc for this would have been your products, which are Hi, and there's a coefficient, so we've got to square that, over your reactants, H2 and I2. And then you would have gone on and done your problem, however the problem was. If you're doing Kp, it's still the exact same thing, products over reactants, but we can't use square brackets. If you remember, square brackets mean molarity. We're doing pressures. So instead, it's going to be a capital P for pressure. It's going to be the pressure of Hi, and that will be squared, just like this one over here was squared. And it will be over, I almost did a square bracket, pressure of H2 times the pressure of I2. So it's really the exact same thing. We're just using P's instead of square brackets. Now you might think, well, that's no big deal. I'm just going to use square brackets the whole time. You need to be really careful of that. Sometimes the AP test gives us a point simply for writing this expression, not even doing any work with it, just writing the expression. So we want to make sure we're writing it right. If it was a pressure problem and you use square brackets, they're not going to give you credit, because it's not about pressure, about square brackets, it's not about molarity, it's about pressure. Okay? So other than that, the problems work the exact same way. So we're going to go through, do a couple of different problems so that I can show you that, how they work. We're also in a little while going to see what the relationship between Kc and Kp are, because you can actually find Kc if you know Kp and vice versa for gas phase reactions. So let's go ahead and take a look at this problem. Like we've been learning in class, it's important to read the wording. It says at equilibrium. If it says at equilibrium, we don't need a table. Okay, they're telling us the equilibrium pressures. So all we need to do is plug in to our equilibrium expression. So we're going to do Kp equals, and you have the equation there on your paper. For some reason I don't have it up here on the board. So take your product, which was SO3. So the pressure of SO3, notice SO3 has a coefficient of a 2, so that's going to be squared, times the pressure of S, and then S should be squared. It's got a coefficient, right? And then the pressure of O2, and that one will be cubed. Lots of coefficients in this one. So now we're just going to plug in all our values. They told us the pressure of S was 0.0035, so that goes here. and that one should have been squared. The pressure of SO3 is the top one, so 0.0050, and that one is squared. And then the O2 is here, 0.0021, and that is cubed. Again, we're not using an equilibrium table or anything because they already told us that we were at equilibrium, so we didn't have to figure that part out. So we plug all of that in our calculator. Be careful when you're putting this in. Make sure you have a big parenthesis around everything on the bottom, or else your calculator will misunderstand you. And you end up with 2.2, rounding to 2 sig figs, times 10 to the 8th. Now, like KC, KP does not have a unit. We're talking about how big it is. That's really, or big or small, that's all we really care. So this is just telling us that at equilibrium, there are way more products than reactants for this gas phase reaction in terms of their pressures, okay, the pressure that they're exerting. Okay, so that's the first example. So that was just like the other problems we did, just instead of being given molarities, we're given pressures, but really works exactly the same way. I'm actually noticing something I did weird here. I really should have written this like this, P of O2. There you go. I don't know why I just wrote a big O2. All right, so that's what that one looks like. Let's move on to number 2. It says, using the same equation from problem 1, determine if the following system is in equilibrium. Determine if the following system is in equilibrium. If you see that, determine if the following system is in equilibrium, then this is a Q problem. And we can use Q with KP just like we used Q with KC. So I'm going to call it Q this time instead of KP, because I don't know if I'm at equilibrium. We already wrote this, just rewrite it on this problem. So the pressure of SO3 squared over the pressure of S squared is the pressure of O2 cubed, right? Like that. They gave us all the values for this one. They're all listed right here. So we're going to plug all of those in. So we have 1.25 squared over 0.0122 squared and 0.256 cubed. Okay? And we're going to solve. And we end up with 7.42 times 10 to the 5th. Okay? So our first thing we want to do with this is compare it to what they told us that the KP was. We already figured out the KP in this first problem right here. The KP in the first problem was 2.2. I'm going to write it here. KP was 2.2 times 10 to the 8th. So first, are those the same? Of course, the answer is no. So your first conclusion is we are not at equilibrium. Okay, so it says determine if you are at equilibrium. The answer is no. Then it says if it's not at equilibrium, determine which direction the reaction has to proceed in order to get to equilibrium. So the quick answer is that KP is bigger than Q, so you know that your reaction is going to go to the right. Or you can say is going to produce more product. Or you can say it's going to go in the forward direction. But again, I need you to understand why. So the issue is that Q is too small. Q is too small. I need Q to get bigger. Remember, Q is products over reactants. If I need Q to get bigger, I need products to get bigger. If the reactants get bigger, Q gets smaller, and that's getting further away from our equilibrium point, which is there. Okay, so these are your answers, and again, you need to be able to explain your thoughts. So same type of problem as we did before, KC with Q, we can do KP, just plugging in pressures instead. All right, sample problem, number 3. I don't have it on here. Again, I'm not sure why, but we'll be okay. So we're going to start, let's read the problem. It says sulfur trioxide decomposes at high temperature in a sealed container. They give you our equation. Initially, that's a huge word. Underline it, circle it, star it, draw a little smiley face next to it. Initially means we have to draw a table. Okay, initially means we are being told how it started. Okay, we don't know our equilibrium stuff yet. We are going to have to determine that for ourselves. So we're going to draw our table like so. We're going to put in our equation, which is 2SO3, and it's in equilibrium with 2SO2 and an O2. Okay, we're going to plug in our concentration. So it said initially it has, oh, I'm sorry, we're going to plug in our pressures because we're doing Kp. So initially it has a pressure of 0.5. Okay, its pressure's unit doesn't matter as long as it's consistent. You'll notice we'll use ATM most of the time, but as long as it's consistent, it doesn't make a difference. They didn't tell us anything about SO2 or O2, which means there's none to start with. Now, before we even finish looking at what the problem wants us to do, let's fill out the table. You're going to have x's. You're going to bring your coefficients down and make one side positive and one side negative. I'm going to make the 0 side positive and negative. I'm going to add, just like we did before. From here on out, you won't even know that it's about pressure, really, because all you need are the numbers. So there's what we have so far. Now let's read what else is given. It says, at equilibrium, the SO3 partial pressure is 0.2 atm. They just told us the answer to the SO3. They told us that this was 0.2 atm. Remember, they said it was about the SO3. So this is one of those problems where we get to do it pretty straightforward. This box equals this box. So we're going to do 0.2 equals 0.5 minus 2x and solve. So we're going to subtract over. We'll end up with, we'll leave negative 2x over here. If we subtract over the 0.5, we get negative 0.3. And we divide over the negative 2. Sorry, that point is getting weird. And x ends up equaling 0.150. Now I'm going to come back up here. I'm going to plug my x in. That one's easy, 0.150. And again, the unit is atm because we're back in pressure this time. And then 2 times that would, of course, be 0.300. And you can check these problems the same way. Take all these values, plug them into the Kp expression, and solve. You should end up with the same Kp as we had before. Oh, wait, they didn't even give us Kp. Well, that was silly. I'm not even reading the question. It says calculate the value of Kp. Oh, look at me. Such a bad role model sometimes. So Kp is going to be the product's pressures over the reactant's pressures. So the pressure of SO2, and that will be squared, times the pressure of O2, only to the first, and then the pressure of SO3 squared. We're solving for Kp, so we're going to put in the pressure of SO2, which is 0.3, and that's going to be squared. And then we're going to put in the pressure of O2. You guys deserve better than that nastiness. You know what? I'm erasing that one too. Ah! Okay, guys, it's getting a little ridiculous. Aren't you wishing about now that I knew how to edit? Me too. All right, so again, so Kp is going to be SO2's pressure, which was 0.3 squared, O2's pressure, which is 0.15, and then SO3's, which was 0.2 squared. Plug all of that into your calculator, and you get a Kp of 0.338. Okay. So I hate to say it too much, but it's the same thing as we did before, but with pressures instead of concentrations. Okay. All right, so if you need to go back and rewatch any of those, obviously do. Now, I told you that there's a relationship between Kp and Kc, and this is actually the equation that relates those two to each other. So Kp is equal to Kc, but only when it's times RT raised to the delta Ng. So let me explain your variables. You know Kp, you know Kc. R is 0.08206. Remember, R is always 0.08206 when you're dealing with gases. And the unit is liters times atmospheres over moles times Kelvin. Okay, that's our unit on there. Now T is obviously temperature, but we have to have it in Kelvin because of this right here. And then delta Ng means change in moles. That's what N is moles, but of the gas substances only. So if you look on your paper, it's telling you that this delta Ng, do this over here, is equal to the moles of gas product minus the moles of gas reactants. Okay, and the way that you're going to get that is from the coefficients. Okay, the coefficients in the balanced equation tell you the relative number of moles. Okay, and you can use those to figure out your delta Ng. So let me show you how this works. Be careful and make sure, by the way, that delta Ng is a power on that RT. You're not multiplying by it, it's raised to that power. Okay, so here's a problem. It says calculate Kp for the following reaction at 100 degrees Celsius. They give us the equation, they give us Kc. Okay, the first thing you're going to want to do, and I'm not going to tell you this in homeworks or on quizzes, but first step is to figure out what delta Ng is. So delta Ng is moles of product minus moles of reactant, but only for gases. So look at your phases, make sure they're all gases. So you're going to have 2 moles of gas product, and then here you have 1 and 1 makes 2. So delta Ng on this problem comes out to be 0. So again, I got 2 from my product. I had 1 and 1 on my reactants, so 2 minus 2 is 0. So I'm going to plug into my equation. So my equation, we have right above Kp equals Kc. They told me Kc was 49. I have that right here. It's going to be times R, 0.08206, times Kelvin temperature, so add 273 to that 100, 373, and it's raised to the 0 power. Now, as you remember, we spent a lot of time with the 0 power friend in rate law. If you raise something to 0 power, it cancels it out. So it cancels all of this, not the 49, because that's not part of that parenthesis, but it cancels all of this out. So in this problem, Kp equals the same thing that Kc did at 49. And the reason why that was, why it equaled Kc, it doesn't always. The reason why it did was because the change in moles of gas was 0. So the pressure and the molarity relationships were the same. Okay. Now let me show you one where it doesn't do that. So let's do this one. It says calculate Kc for the following reaction. So we're going to do, let's write down our equation. Kp equals Kc times RT delta Ng. And I know right now you're all thinking, do I need to memorize that equation? And I am thinking I have no clue because I don't have your equation sheet memorized. So I'm looking at your equation sheet and I do not see it. Do 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 do. No, don't see it. So yes, okay. You do need to make sure you know it. So Kp is equal to 2.2 times 10 to the 8th. That equals, because I know Kp, now I'm trying to solve for Kc. There's my variable. R is 0.08206. Temperature 5, already given in Kelvin at 573. Now my change in moles of gas. So I have 2 for product. Do my work right here. So 2 minus, over here, both of these are gases. So I have 2 and 3. So it's going to be 2 minus 5. So it gives me a -3. And no, you don't have to show me this part of your work. You can do that in your head. So this comes out to be -3. So that could be a positive number or a negative number, or it can be 0, like we saw in the last problem. And then we go ahead and plug that in. If you plug that in your calculator, you should end up with 2.3 times 10 to the 13th. And I wrote Kc, yep. So we just used Kp to figure out what Kc was. Okay. Now, if you look at that, I don't think, I'm not sure what I can tell you about where you'll make a mistake. I think from grading things, this is usually where people make their mistake. Just make sure you pay attention to whether or not your substances are gases. If this had said solid right here, like that, then you would have ignored this one altogether. You would have done 2 minus 3, and it would have been -1. So make sure you're paying attention, because it's only the gases that matter for the Kp conversions. So take a look, work on those homework problems.